Right, guys, I think after we've looked at the new radian measure of angles, I think it's necessary that we discuss trigonometric functions. And my idea is I'm going to discuss, focus on the sine curve. I think I told you about this yesterday. Let's say we've got sine A sine t. And now, from today onwards, when I'm using t there, you must understand that that t is in radians. Altogether. Actually, I don't want sine t, I want sine omega t. Something like that. This omega t is what I can call the argument of this sine curve. Is that right? Okay. But I'm not going to start there. We're going to start here, where we've got y sine t. I've got two things at the top there. On this first line here, I've got a, call that amplitude. I'll just write AMPL, call that amplitude. And then I've got another parameter, which is omega, call that angular velocity. I'll just write the AV, angular velocity. So what we're going to discuss now is to see the influence of those parameters. When you change them, what happens to the curve altogether. By so doing, we'll be trying to get into the better understanding of the curve, in such that when we just flash our eyes on a version of that, we can just imagine what happens and be able to describe what happens where this moves this way or that. Altogether, guys. Okay. Now, looking at this one, I will say this is the simplest version of the sine curve. Then there, A is 1. Omega is 1. That is very important. And also, I will assume that everybody using degrees, you have known that this function has got this shape. Where there is 180 and there is 360. But today we moved away from that. This is 2 pi and this is what? 1 pi. And this is 0. And this oscillates between -1 and 1. I normally give a name to this function and say this is actually the life function. The sine function is the life function. If you go to hospital or you get knocked down by a car, they put an oscilloscope on you to check whether you're still alive. You will see a sine curve going up and down. Once you see it straight, you know where to go to. All together. So that's a life function. I'm still going to show you how more it is a life function later. That's all right. Okay. So now let's start. Let's have a horizontal axis there. And our vertical. And just choose an arbitrary scale and say this is what? Pi. And there, and say this is what? 2 pi. And there, 3 pi. And then there, 4 pi. And now this, we're going to call it t to replace our independent variable x and t. And this is going to be our function y, the values there. Let's maybe mark there and say this is 1. And then this is -1. Now guys, let's look at this function very carefully. You know, when you are going to sketch any curve, it's very important, not only sine curve, it's very important that you highlight the notable functions. Sometimes people say critical points of the curve, those decisive points of the curve, which you must not, like for example, the intercept on y, the zeros and blah blah. So here, we're going to highlight the zeros of this function. Let's say zeros, they're going to be important when we plot the graph. Or let's say different versions of the graph, of the function. Zeros are at 0, at pi, at 2 pi. And as I said, the function is going to come in different versions with different parameters there. But these ones, for the standard, for the simplest one, they are the controlling ones. They are you can use them as a kind of control. Those are zeros. Then the next thing, I want to call turning points. Let's just write there, TP. TP, turning point, I mean here, where the function was rising, then suddenly it's going down. So meaning somewhere here, there's a turning point, and it's halfway pi. So then let's call that half pi. Then the turning points are at half pi, and then at somewhere there, after two halves is pi, then there is going to be 3 halves of pi. All together, guys? Okay. Now these are going to be very, very important. Now, I think everybody can imagine here that if we insert this curve here, the simplest curve, everybody can see that this curve is going to go up, down, 0, minimum point, then up, then it continues this way. And we assume that this curve, when you see it at t is equal to 0 here, at t equal to 0, it's actually where we start seeing it, but otherwise it comes from t minus infinity. So somewhere there, we've got minus pi and that. So it's actually, we can just look at it as an infinite oscillation from time minus infinity to infinity. All together? I know somewhere it's written at the beginning, but time is not beginning. So when we talk about the beginning, we're talking about the beginning of an experiment, of certain experiment. All together. But otherwise, time is not beginning, because when you say at the beginning, there's time before the beginning. All together? Yeah. So be careful there. If that shakes your beliefs, you can revise them. It's not a problem. Right. So that's the thing. Now, what I want to do now, I want to look at a variation of this curve and look at something which says y equals to 2 sine t. All together. Now notice, the only thing which has changed is a. If I just erase this 2, I will have sine, which means the zeros, the turning points are going to be the same. Is that clear to everyone? But what's going to change? When you get to this value, for example, let's look at this value, half pi here. The function is supposed to be 1, but instead of being 1, that 1 is going to multiply by 2. So which means now, the curve, instead of turning at this level, is going to turn at that level. How to work, guys? Then when you come this side also, something similar is going to happen. Let's say minus 2 here. Instead of turning here at roughly 1, it's going to turn there at 2. And then the rest of the values in between are going to be raised by multiplication by 2 in a similar fashion. Is that understood? Now, let's insert that graph now. That graph will be this. Normally, when you draw this graph, you must stop breathing a bit. Just hold your breath, because if you breathe, you get it wrong. All together. All together. Okay. So, if we look at it as a wave, it just tells us that when the amplitude is higher, the waves are higher, isn't it? So if you are looking at the C will be rough. But now let's look at another version. Let's look at another version which says y equals to half sine t. Again, it's the same case because sine t, the zeros are same, but half t. What's going to happen now? At the same point where the function is going to be 1, it's going to multiply by half. Then the function will turn somewhere there. Half is somewhere there. This side, same story. It's going to turn there. Now let's look at that kind of function. It's going to go do you see what's happening, guys? The amplitude has been smaller, the wave height becomes smaller. Altogether, you know, the waves are not as rough as they were when we were 2. Altogether. So that is the influence of changing this parameter here called the amplitude. Altogether, guys. Okay. Any questions at that point? Any clarifications? Yes. We multiply the value of the function, like for example, at half pi, the value of the function will be 1. But it says the sine value, sine at t, multiplied by 2. So then we multiply by 2, then it shoots up to there, to 2. Am I making myself clear? Everybody? Okay? Another question? Right. Given the situation that there are no questions at the moment, then I think let's move to the influence of what? The angular velocity. What we want to look at now, let's look at the situation where we've got y is equals to sine half t. So now the angular velocity, omega, is equals to half. We want to see what is going to happen. Now, at this point, we really need to look at our zeros and turning points very carefully. Now, let's check what's going to happen. Let's check what's going to happen. At this, when you look at this simplest version, y is equal to sine t. We can consider from t equal to 0, our first 0 is at 0, our second 0 is at pi, the third one is at 2 pi. All together? Okay. Now, let's see. Let's say zeros. I'm doing what I could call the analysis of this function now. Zeros. What I'm going to do, let's now not say it's 0 when t is equal to 0. Let's say it's 0 when the argument is equal to 0. Do you understand the change of how I use my words? I'm saying they were looking about sine t. Now we're looking at sine half t. But if I look at sine t, I could have said when t is equal to 0. But I want to avoid that because I think that thing is introducing some bit of noise there. Let's use the word which says it's 0 when the argument is equal to 0. What am I saying here? I'm going to say the argument here is this. So I'm saying this function, like the mother function, is going to be 0 when its argument is equal to 0. So the first 0 is going to occur when half t is equal to 0. Therefore, t is equal to 0. Do you agree to me there? So 0. So we agree. It's going to start there. Okay. Then the next 0 will be at pi, isn't it? Then we say it will be 0 when this argument is equal to pi. Now the argument is half t equals to pi. Then we solve this equation. This equation says therefore t is equals to 2 pi, which means the next 0 will be somewhere there. I think you can feel already what's happening, eh? Okay. Then the last one, the last 0, it will be 0 when the argument, I always talk of the argument in this case, when the argument is equals to 2 pi. Then when I solve that equation, this says t is equals to 4 pi. You see, already I've put my 4 pi here as if I had a professor. Our amplitude is what? Is 1. It's not a problem, is it? Let's have our turning points now. Turning points, exactly the same argument. Let me just do this a bit here. Let me erase this. I've represented my zeros. At 0, the value of the function is 0, so you just plot that point on the y-axis. Now, let's talk about turning points. Let's talk about, just for turning points, I just write TP. So where are the turning points? The turning points are when the argument is half pi. So I say argument half t must be equals to half pi. Then I solve that equation. What's the answer? T is equal to pi. So the turning point will be here. And normally, because the argument is the amplitude is 1, then which means at that point the function will be at level 1. Do you agree? Then next turning point is when the argument is equals to 3/2 of pi, isn't it? Then I solve that equation. Then I get that is 3 pi. That will be somewhere here. And at that point is the lowest point you can get is somewhere there. Now, I think now we must plug in the cave. Let's take another color just to see it clearly. Now it's going to rise from there. And go this way. The next 0 was where? At 2 pi, isn't it? Right. Something which I have not mentioned. If we start from 0 there up to 2 pi, we say we've completed one cycle. One cycle. But look at this. This one, from 0 to 2 pi, it has actually completed half a cycle. Why? The angular velocity is slower. Then it takes time to cover up what it covered with the other higher one, which was 1. So then it continues there. Now as down up to the lowest point, then rising up to there, then it continues periodically. I'm using there the word periodic. I don't know whether everybody understands what I'm talking about. I'm saying this function is periodic, meaning it repeats itself every fixed period. In this case, the standard one, this one, is period t equals to 2 pi. Do you understand that? Okay. But this one, it looks, each cycle is completed at what? At 4 pi. Then it repeats itself. Now, I hope now you have understood what's the influence of this angular velocity there, isn't it? But maybe to understand it better, let's put another one with a different angular velocity. Let me say, let's say we put this one. I'm going to ask you to calculate the zeros for me yourselves quickly and give me the answers, and I just plot them. Each one of you is going to calculate the zeros. Now the function is y is equal to sine 2t. Can I have the first 0? First 0? I hope you are calculating it, isn't it? So the first 0 will be t equals to 0. Next 0, t equals to half pi. I hope you are applying what we discussed before, isn't it? Next 0, pi. That is those are the 3 zeros within the first cycle, isn't it? They don't know what's going to happen. Now the turning points. Quarter, pi, and 3/4 of pi, isn't it? So let's plot them. The first one, the 0 is at there and there. And the last one is here. No, sorry, there at pi, isn't it? Then the turning points, the first one is at quarter pi, which is there. I'm not going to write quarter pi there, I'm just going to mark it. Then it's going to be there 1. Then the next one is 3/4 pi, somewhere in between there. It's going to be that. Then getting the curve in, this color thing is not working very well for me. Then the curve will be the ambulance is moving. Altogether, there is the thing. Now you can compare the two. When the angular velocity is small, it takes a lot of time to stretch to complete the period. When it's high, it takes almost half. Now you can go, this is 1, this is half, and this is 2. Now you can see what happens when I manipulate the thing. So what have I done here? I first of all isolated the amplitude. You have experienced the amplitude, isn't it? And then isolated the angular velocity. Then what can I do now? In the next step, I can combine. Now it's what I'm talking about now. I can have an equation now, which I can ask you to discuss, which is 3 sine 4t. You must be able to go and sit down and do exactly the same kind of discussion and be able to sketch this curve and talk about it, that what has happened is this and this and this is demonstrated where, or is illustrated by the curve. Who says I can do that? Let's hands up who says I can do that. I think that is going to be in the second class test. Appointment. That's an appointment. All together. Okay. So guys, are you fine then? Okay. Now, this kind of discussion, I'm inviting you to take it to sine, to tangent, and to the rest of the trigonometric functions, isn't it? But before I get there, let's talk about another variation. Now let's look at this kind of a sine curve. Let's say we've got y is equals to sine t minus pi. Now, what you can see that now before I had a multiplying, like a multiplying t, but now I've subtracting pi on t. We need to see what is the influence of that. Altogether, our standard curve there, our simplest curve there before was just y equals to a sine omega t. Now if I've got this one, it's like I've got y is equals to a sine omega, maybe let's say t minus, let's put this thing there, more or less something like that, but I didn't really want it like that. Let's say omega t minus what? Minus pi. Let's move this thing. I want to say, write it this way, omega t minus that, and then we can also remove that. So what happens here? In this case, our omega is 1, and we've got our pi there, and then we've got amplitude is that there. Maybe let me put pi here. Maybe it's going to confuse it. Let me just put any other number. Maybe let me put here alpha. Altogether. So we notice that omega in this case is 1, pi is our alpha then. So we want to see what's going to happen. Let's give our horizontal axis there. And then let's have our vertical. And then we've got 1 pi, 2, 3, 4. There we have it. And then we've got 0 here. Then let's put also maybe minus pi there. Now, our standard curve, we know, is going to be z, then continue there, continue there. Now, let's analyze this one now and start with our zeros. Then we say this function, like the mother function sine t, is going to have a 0 when its argument is equal to 0. So we are saying argument is t minus that equals to 0. Then we get this, that. All together. Okay. So, please, I hope you don't take offense from me saying the mother function or whatever. Because at the end of the day, when everybody else is gone, we are left with our mothers. Is that fine? So everybody doesn't get an offense from that. So our first 0 is at pi, which means the new function we're discussing here is going, our first experience of a 0 after t equals is going to be here. So it's going to shoot up here, like that one was shooting up there. Do you understand what has happened? It looks like that 0 has been delayed by pi. Do you see that? Before it occurred here, but now because of the way the equation came, it occurs there. Now the next 0, it will occur when the argument t minus pi is equals to pi. Solving that, it gets us t equals to 2 pi. Then, which means our next 0 is going to be there. Then the last one is argument that equals to 2 pi. We say our t is equal to 3 pi. So our next 0 is going to be there. All together, guys. Now let's come to our turning points. Turning points happen first when our argument is equal to half pi. We're talking about the mother graph sine t. Is that right? So then, which means now this one also will take after the mother and say, okay, I'll wait also until my argument is half pi for me to have a turning point. Then when we manipulate that equation, it tells us that t is equal to 3 halves of pi. Is that right? 3 halves of pi. If you don't get what that is, pi here is 2 halves. Then we add on both sides pi, we get 3 halves of pi. Right. The next thing is when the argument is equals to 3 halves of pi. Is that right? Then when I do the same thing, I get to t equals to 5 halves of pi. Where is 2 halves of pi? 3 halves of pi is here, which means the function will be there at the highest point. 5 halves of pi, this is 4 halves of pi, 5 halves of pi will be there. Then the function will be there at the lowest point. Now inserting that graph, which means it's going to have then it continues vertically then it will come down this way. Something like that. So now this lap was delayed, is the one which is occurring there. And then we say there's a phase shift. What we could say here, a horizontal translation of the curve to the right. So from there now, you must take this discussion to what will happen if you've got sine 2t, maybe minus half, or let's say plus half pi. The discussion we did here is exactly the same thing. Take the argument, compare it to the mother function, and they always manipulate. Then you get your plot your points, then you go on and you get exactly what you want. Am I making myself clear? Can I say that is understood? Is there any question or anything which you want to clarify? Don't be afraid. Just ask. Remember I said there's no stupid question. A question is a question. All together. You want to say something? Yes? No? Okay. If there's no one who wants to say something, I'll move forward and say, okay, thank you. Up to that point. Let's carry on our next discussion later.